Thank you, James. I'm going to be talking about energy and start with the concept that ought to be patently obvious to everybody, that energy drives everything. Whenever you shape something, move something, heat something, such as either heating your house, melting some metal, or cooking your food, you cool something, such as refrigerating milk and so forth, or you grow something, in short, do anything to anything, energy is required. I think James made this point a while ago, but it won't hurt to remake it. Energy is the lifeblood of civilization. Back in the, I don't know, it's probably 80s, 90s, something like that, the term appropriate technology came along. You know, people ought to be using the appropriate technology. Here are a couple of examples. Women carrying water on their heads from, where did they get that water? And they're delivering it to their homes to use, and then people cooking over open fires in their little huts and so forth with deadly consequences. That was appropriate technology. Now here is a graph showing the link between poverty and electricity access. Toward the left is increasing poverty. And you see a bunch of countries over there, such as Nigeria, Nepal, Madagascar, Mozambique, Ghana, Senegal, and so forth, where a great number of their population lives below, or exists on below $2 a day. And the vertical axis represents how much access they have to electricity. Notice that OECD is way up there at the upper right, Canada, United States, and so forth. So we have very few people who are living in great poverty, and there's a whole lot of electricity available. But something like 1.6 billion people, a quarter of the world's population, has no access to electricity. Now, let me point out something here, that if the amount of mineral resource per capita were the determinant of success, then the Belgian Congo, or the Congo now, would be the richest country on earth, and second would be Russia. So it is the combination of political, economic, social, and so forth activities, so to speak, that are that keep these countries impoverished. Those people are here today trying to impoverish the rich countries. And I would like to make a point that we are not talking about a question of profits versus the environment, as some of those people will try to make. This graph right in here shows you the life expectancy at birth versus the energy consumption. You'll notice that the life expectancy increases as the amount of energy is consumed. This is sort of on a country-by-country basis. Nevertheless, energy is routinely opposed by groups lovingly calling themselves environmentalists. We'll begin at the upper left with coal. People are opposed to coal. Now, actually, you can burn coal very cleanly in a big power plant if you decide to go that way, but you cannot burn it cleanly in your household furnace, but you can do it on a large scale. People are opposed to oil exploration, oil delivery. They're opposed to natural gas. They're opposed to nuclear. They're opposed to hydro. They're opposed to big wind installations. The reason they aren't now so much is that, well, it's out there in the West where there's just flyover country, and aren't those cute little windmills cute? But on the other hand, they do manage to kill lots of raptors. Solar, opposed by environmentalists. Would you believe right now that in Massachusetts, people are proposing cutting down forests so that the trees do not shade their precious little solar collectors? And this last one's kind of a cute thing here. A number of years ago, there was a power plant, a nuclear power plant in California, which they shut down in favor of that pathetic little solar collector there. They occupied equal amounts of area, and the solar collectors, produced 1/1000th as much power as the nuclear reactor did. Well, how about, they're opposed to energy, but they're also opposed to energy transmission. They're opposed to railroad cars carrying coal. They're opposed to pipelines. They are opposed to ships carrying oil. They are opposed to tank trucks carrying oil. They are opposed to tank cars on railways carrying oil. And God forbid you should take a little bit of waste casket away from a nuclear power plant and send it off to Nevada, where Harry Reid has blocked the project to store that waste. And of course, they are opposed to liquid natural gas tankers. Incidentally, Hawaii would benefit very greatly if they had a liquefied natural gas terminal where people could ship natural gas from the United States, where it's very abundant, over to the other part of the United States, Hawaii. But that is opposed. It is illegal because of the Jones Act, which forbids a tanker or a ship to go from one American port to another American port unless the ship is made in the United States and manned by Americans. There's, of course, energy uses that are opposed, and don't pretend that this is a definitive list, but these environmentalists are opposed to things like air conditioning. Bet you $5 you can't find anybody over at the UN conference that has turned down, has opted for hot Salt Lake City air. They're opposed to transportation by automobiles. They're opposed to transportation by airplanes. Turn down your thermostat, they say, and God forbid, don't eat meat. And as far as regular vegetables are concerned, well, you just are not permitted to bring in vegetables from some great distance because it might involve using fuels. Oh, and what about electrical transmission? What you have to do to transmit electricity from place to place over great distances is to jack the voltage up to a very high voltage. If you go up by a factor of 1,000, you cut down the line power losses by a factor of 1,000,000, which is why they do it. And you will want to remember this a little bit later on, but all of that stuff is in the NIMBY category, not in my backyard. Now, I have a list here. James had a colorful list. Mine's simply just a list, but I'm going to be talking about goal number 7 there, which is affordable and clean energy. The UN sustainability goals, or is it unsustainability goals? I'm not sure. By 2030, and I'm quoting exactly, the plan is to ensure universal access to affordable, reliable, and modern energy services. Who could oppose that? Unfortunately, They all do. But what they want to do is to increase the share of renewable energy by a great amount, double the growth. Read this carefully. By 2030, double the global rate of improvement in energy efficiency. They're going to double the derivative of the efficiency with respect to time. Now what? What in thunder do they mean? But anyway, they wouldn't understand it anyway. Okay, again, they want clean energy research, renewable energy, energy efficiency, and cleaner fossil fuel technology. By the way, you may not know this, but in the United States at least, we presently use about 3.5 times as much energy per capita. That's only 3.5 times as much energy per capita as our 1700s ancestors who did not have cars, trains, airplanes, electricity. They didn't have any of that stuff. So we have achieved that by virtue of making continual improvements in energy efficiency. So we don't need a lecture about it. So they want to expand the infrastructure. Well, infrastructure, you remember what infrastructure looks like, those high voltage power lines? Okay, they want to do that, except they won't. And of course, they say not a word about nuclear. I'm going to point out to you that the renewals aren't doing the job. Here's a graph showing the annual world energy demand. And it goes from about 1970 or so up to 2015. It shows the graph of the primary supply by fuel. And down at the bottom, the brown is coal. The fairly light blue is oil. The darker blue is natural gas. Nuclear comes along with that kind of orangey color. Hydro, biofuels and waste, which is the green stuff, and other means pretty much solar and wind, and to some extent geothermal. You'll notice that they barely show up. That's world energy demand. Okay, we'll go to the United States. Here's a graph showing a chart showing the energy flow in the United States in 2018. It comes from the Energy Information Administration. And here is the renewable energy, that little bit down at the bottom, and it is mostly hydro and wood. Hydro is renewable energy, okay? Okay, there's another graph showing sort of the same thing, but it's got petroleum, natural gas, and coal, nuclear, biomass, other renewables, aka solar and wind, and hydroelectricity down there. You notice the hydro is fairly stable, and that's simply because we have pretty much used up all of the really good hydro sites. That graph goes 1776 to 2018. Here's a plot of the electricity flow. And way over here in the lower left corner is a thing called renewable energy, which is a very, very small fraction of the electricity flow. This is showing the renewable energy consumption on a fuel-by-fuel basis. There's hydropower in the light blue, biomass, which includes some ethanol and mostly firewood and that kind of stuff. Wind and solar down there in the lower right. The horizontal line represents 2 quads. That's a quadrillion BTUs. But the annual consumption in the United States is about 100 quads. Another way of showing it, again, the vertical axis is in quads. The fossil fuels are way up there, running over 80% of our consumption. Nuclear power down there, and the sum of all renewables, including hydro and wood, is running along there way down low. And renewables aren't doing the job in spite of massive subsidies. To give you an idea, here's the effectiveness of subsidies. These are in 2010 dollars per megawatt hour. In other words, how much subsidy is given per unit of useful electricity. And solar it's not to scale there. If we drew that line up to scale, it would go up to about the 3rd or 4th floor of this building. They had a tremendous amount of subsidy with very, very little output. And there's a subsidy that isn't listed here, and that is that solar and wind are, to repeat, very, very unreliable, and they have to be backed up by reliable power sources. And those power sources are running at lower efficiency than they could because they're driving in heavy traffic, so to speak, accelerating, stopping, accelerating, and stopping, and so forth. There's a huge subsidy provided by those. And I make this comment here, and I want you to understand the veracity of it. Without backup and storage, solar and wind are basically worthless. Remember that. You can't run a factory. You can't run transportation. You can't run most things on solar and wind because they're so variable. So I'm going to class a few icons, if you don't mind, about free renewable energy. I want you to think about this. Can you buy a kilowatt hour of midnight solar energy for $1 million? Can you buy a kilowatt hour of wind-generated electricity when the air is calm for $1 million? By the way, when I first learned about kilowatts and kilowatt hours in the 8th grade, the price of a kilowatt hour of electricity where I lived in Aurora, Colorado was 4 cents, and the price of a candy bar was a nickel. The U.S. average price of electricity these days is around 12 or 13 cents per kilowatt hour. You ever looked at a price of a candy bar recently? Okay. Whoops, I did something wrong here. Okay, there it goes. Wrong button. Okay, now here are the knee-jerk, reflexive lizard brain answers. Hey, you can store solar energy during the day and use it at night, so midnight solar energy is available and cheap. And the other one is, well, the wind is always blowing somewhere, and besides, there's storage. But we're going to have a closer look at those, and we're going to choose some never-pondered questions. Numbers. How much energy storage is required for an all-renewable system? How many days storage do you need to get 99.9% reliability, which is what we have with our current grid? You're going to store energy for 5 days, maybe? The wind can be calm for a long time. You can have cloudy weather for a long time. Of course, no sunshine at night. And then the related thing is how much power is required to charge the storage system during the times when the solar and wind system produces power. All right, you got some power. How much are you going to have to charge up the storage system that's going to last you several days? And then how much power must the storage system be able to deliver? So I'm going to give you an example. This is from California's demand curve. And I want you to look at the lower left. You see that color blue in there? That's called base load. That's run by natural gas combined cycle, by coal, and by nuclear. Very little nuclear in California, I'm afraid. In any case, that's what's called base load. The light green in there is called the intermediate load. And then there's a peak load up there shown in orange, and the curve on a day-by-day basis looks rather as you see it there. In this case, we're talking about California, and these curves are rather typical of what's in the industry. The system average demand is 35 gigawatts. A giga is 1,000 megawatts. The maximum is up to 41. Okay, but if we're going to be storing enough energy to last for one day, we have to have 210 gigawatts of available solar power. Okay? 35 gigawatts for immediate storage or for immediate needs, and 175 gigawatts for storage. The energy consumed during the 4 hours is 140 gigawatt hours. The energy that is stored must be 700 gigawatt hours. And that's for one day. Now we're going to take a look at wind. And this one is, the black line there is the power curve for wind. You notice that at a speed below about 4.5 meters per second, which is in the range of 10 miles an hour. The blue lines there represent speeds in miles per hour. On the lower scale, it's in meters per second. Below about 4.5 meters per second, you get no power whatsoever. Then the unit turns on and you start getting some power. And in the range of, around 5.5 up to about 13, 14 meters per second, there's a very, very dramatic rise. A 10% change in the wind speed results in a 30% change in the power, or a change in wind speed from, let's say, 10 miles an hour up to 20 miles an hour gives you a factor of 8 in the amount of power. And it's very hard to keep the line stable when you've got variable wind. Over half the time you're producing less than half of the nameplate power, and only 11% of the time are you producing full power. This curve that looks a little bit like a distorted bell curve is the wind profile at an outstanding site, 700 watts per square meter in the wind. And the scale on the right is the number of half hours per year that you get wind at various speeds. So you see, the wind is a pretty unreliable thing. And this one shows you just a chart of something like 24 hours. That's what the wind looks like. And that's in all of Texas put together. Now, for one day storage wind, you don't have things quite as dramatically, because you get wind for a larger fraction of the time than you get solar. But the wind machines are designed for an annual capacity factor of 35%. That means if your nameplate says you are going to generate 1 megawatt, you're on average going to get 350 kilowatts. And another problem about wind is that the amount of power you can produce per unit area of land is about 5 kilowatts per acre, or 12.5 kilowatts per hectare of land in excellent sites. And to produce an average power of a gigawatt, which would handle about a city of 700,000, you have to have 300 square miles. Okay, this is a better way to run a zoo. Suppose that you, instead of using your nukes and your coal and your combined cycle natural gas, instead of using it just to produce the base load, you increase it to produce average load. Okay, so you increase it from 24 up to 35 gigawatts in this case. What you can do then is store some energy during the time, say midnight to a few hours in the morning or something like that, when you have lower power demand. You store that energy and you can release it in the afternoon and so forth. The storage requirement is about a fourth of 1 day's energy, and the storage power requirement is about 1/4 of the average power. So here are the requirements for getting something like 99.9% reliability. First line there, for solar and wind, you have to store something like 5 days worth of energy. But with the enhanced base load, you have to store 1/4 of 1 day's energy. So solar and wind is worse by a factor of about 20. Next line down, you have to have 20 to 30 times the average charging power in order to charge up your system to last for days. With the enhanced base load, you only have to have about 1/4 of the average power, and therefore the solar and wind is worse by a factor of somewhere around 80 to 120. Now, solar and wind, you have to have 100% of peak power available from storage, and if you just have enhanced base load, you only have to have about 1/4 of the average power from storage, and so solar and wind is worse by a factor of only 4 in that case. Oh, and we should talk about efficiency, but we won't, because you lose energy when you charge up a system, and you lose energy when you when you discharge it and so forth. Okay, comes the argument, well, it's always available somewhere. Okay, the sun is shining in Arizona, the power is needed in Philadelphia. The wind is blowing in North Dakota, power is needed in Los Angeles. You have high winds in Florida, but Chicago needs power. Each location there must be able to supply enough power for more or less everywhere. And of course, you need one heck of an enhancement of the grid. Now, to make a case here, Mark Jacobson and Mark DELUCCHI at Stanford say this, and I quote exactly: "We estimate that around 3,800,000 5-megawatt wind turbines, 490,300 megawatt concentrated solar plants, 40,300 megawatt solar PV power plants, 1.7 billion 3-kilowatt rooftop PV systems, 5,350 100 megawatt geothermal power plants, 270 1,300 megawatt hydroelectric power plants, 720,000 0.75 megawatt wave devices, and 490,000 1 megawatt tidal turbines can power a 2030 worldwide WWS, whatever system is, world, that uses electricity and electrolytic hydrogen for all purposes." Does anybody know how many different power generators we have in the United States? Something like 8,000. To bring up another beautiful idea from the earlier on, small is beautiful. Okay, they do miss a few things like the amount of storage that's required and how they're going to distribute all this power. And are they thinking of transmission lines from the Gobi Desert to New York City? Well, I guess you'd say if you can walk to Hawaii, I guess you can do that. Now, the good stuff. Get rid of these utopian delusions. There is so much coal available that nobody worries about running out for at least hundreds of years. Now, hundreds of years is a short time compared to that of civilization, but they don't even look for coal because nobody even looks for it anymore. There's enough natural gas in methane clathrates on the continental shelf to last for at least thousands of years. There's enough uranium to last until the sun turns into a red giant, and there's even more thorium. There's no shortage of energy, and there never will be. What we lack is the will to use it and the freedom to use it. Thanks for listening.